What's up, guys? Kristen Ninja here, and this is this is the final study session before the exam. Um, I've sent out the link to a few of my friends. Um, I hope y'all are here, or I hope they end up joining. Because it's lonely studying by yourself, but I'm not really by myself. I got y'all with me. So, with that being said, um, we're just gonna hop right into this. So this is live. Just a reminder that this is live. Wait, hold up. On private videos, hold up. Wait a second. Hold up. I just noticed something. Hold up. This video is private. Hold up. See, this is why see, no, this should be public. Yeah, this should be public. This video is not made for kids, but it should be public. I mean, like kids can watch it if they want, but like they are not gonna understand this like at all. I can guarantee y'all that right this moment. Kids are not gonna understand this. So I'm gonna go prepare myself mentally. I will be back in like 2 minutes. I also gotta take my trash out. So I don't know why I didn't do this. I was asleep. Okay. I took an exam today. Don't judge me. I was sleeping until 4. Don't judge me. Okay. Relax. But when we get back, we're going to be going over waveguides and how waveguides affect signals and how to get guide wavelengths and things like that. I do have a calculator that calculates all these values and stuff like that. But we'll like really get started like right about 6. Okay, I'll be back. Give me a second. I'll be back. Promise. So 11 years still balling out my head. High school, they see the views. Now they're the ones they calling now. So you're new in town, the show class, we go take a seat and shut your mouth and settle down. Okay, y'all. So we're going to go into our we're gonna go over waveguides today. Um, but first we need to hit boundary conditions. So just to explain boundary conditions to y'all a little bit, um, just to explain boundary conditions, I'm just going to read this off my iPad if I can actually see it and read it because I know my handwriting can be atrocious at times. Um, from the Maxwell equations, uh, they rule how. Oh my gosh, jeez, writing is so bad. Electric. Oh, let me. Oh, yeah. Um, jeez, jeez. Okay. So anyway, from the Maxwell equations, you find the rules of how electric and magnetic fields behave at boundaries between different materials. Um, and so, like for a normal vector component, if you don't know what a normal vector is, you probably just haven't been through enough physics or something like that. So, a normal vector is basically if you have some type of vector, which is if you remember from the movie Despicable Me, you have both direction and magnitude. So this would be a vector on some plane. So this vector here has like a direction of, well, when it shows up, it has a direction of going that way, and we'll say it has like a magnitude of 4. So that's a vector. Um, and then when you get to 3 dimensions, you will be able to see that vectors can have a normal vector, and a normal vector is a vector that is exactly perpendicular to the vector that you drew in the first place. And usually it has a unit length of 1. That's just because you're trying to see where the two components of the vectors come together and become a what's it called? They come together and become perpendicular. I forget how to. I like had it in my head to explain it and then I forgot. Also, I'm gonna call my granddad up real quick, see if he wants to join in. Um, so give me just a second. But like while I see if he's gonna answer the phone or not, I'm gonna go ahead and keep explaining. Then you have your tangential. Hey, granddad. Oh, well, right now I'm on my Zoom and I'm live streaming it. If you wanted to come and learn about waveguides and boundary conditions and more stuff, feel free to hop in. You can ask questions if you want to, but you know, I'm just letting you know. Yeah. Okay, cool. Bye. Love you. The genius Dr. Elder, granddad, will be joining us shortly. He may not say much, but that's just what the oh, you see, I'm over here wondering why it's not showing up for y'all. My goofy self did not draw it in the right notebook. Oh man. So this is a vector, has a direction to there we go, direction to magnitude of 4. So it has a direction going that way. And then you have to have a normal vector, you need to have it's a vector that goes perpendicular to this one and usually has a unit length of 1. So this would be like this would be like 1 here. That whole thing just has to do with how we can relate vectors in space to other vectors in space. But yeah, so that's just how that works. Let me let the squad know, you know. I guess I'll monitor the chat on my phone. Kind of. I I promise you, like I'm not gonna be looking at this too much. Um, but yeah, so we got our give me my give me my charger. I need my charger. There we go. Um, so the tangential vector is just a vector that's tangent to it. You can see it kind of drawn out there. But essentially there are 4 boundary conditions, and this is how waveguides work. So if I do this right here, so there's 4 boundary conditions. The first boundary condition is the electric fields. Um, the electric fields on either side are equivalent and they equal 0, so that they're continuous across the boundary. So epsilon 1, mu 1, and sigma 1 are equal to epsilon 2, mu 2, and sigma 2. And that shows that they're tangential. Um, that's supposed to be HT1. I think that's supposed to be HT1, not like mu T1. So H is a condition of current density at the surface. So there's H1 and there's H2. These two will like subtract from each other, and then O K that's what it is. K is the condition for current. So when you have 2 H's, I believe those are magnetic fields. There's usually a current flow between the 2 plates. Then you have dN1 minus dN2, and that equals power density, or charge density, and that's the difference between the electric flux density in the material, and that creates a charge density on the material. You can see that here with this green. Then you have Bn1 equals Bn2. So the normal component of the magnetic flux densities is continuous. Oh no, I uh so here's my amazingly intelligent grandfather. He's joined in with us. He may not say much, but he's here to learn, which is a beautiful thing. For 2 dielectrics back to back, you'll this all of these apply. So for a dielectric and a perfect conductor has uh perfect conductor has what was it? There's a perfect something. A perfect conductor, I think, has no charge loss. A perfect conductor, an example of a perfect conductor, if you were to get distilled water with nothing in it and then try to run a current through it, there would be no electric flow to charge. There would be no electric flow going through the water, because there's nothing to ionize. There's nothing to connect charge together with it. And that's essentially what this is saying. So this is a perfect conductor, or a perfect dielectric. Yeah, a perfect dielectric. Um, so you can see sigma is infinity, um, and you know just how that kind of works. So find e e2 and its angle. So if e1's 1,000, you could do e1 minus for e1, yeah, minus cosine 60, e1 times cosine 60. That gives you a cosine of 60 is a 1/2. If you remember from your pre-calculus. Um, so E2 is 500 volts per meter. The normal vector is E1 times sine of 60, so that's 865 because it's square root of 3 over 2. So um, E1 and E normal 1 minus E2 and E normal 2 is about, I think, 70. No, that's a P source, power source. Um, and then you have your epsilon and epsilon not epsilon r and epsilon naught, and then you multiply those together, subtract that with E normal, and you get this value, and then you can find the magnitude of this with the square root of these two values added together, and you get 708.8 volts per meter. Um, so that's kind of how that works. I believe that the formula should be given if necessary on the formula sheet that we'll have for this exam. So I'm banking on that formula sheet. I'm really banking on it. So I got a little distracted in class while our professor was talking about like not something extremely important. Um, like he was going over the different types of materials or something. It was something that didn't need to be written down. It was not conceptual. It had no bearing on the class itself. So I ended up drawing this cool little doodle. Um, but um, this is essentially talking about how electromagnetic fields have different modes. So you have a transverse electric mode, and you have a transverse magnetic mode, or a TE and TM modes. Um, so with a coaxial cable, both E and H are transverse. So you see TEMN, that should be MN, not NN. M comes first in these scenarios. And they're integers indicating the mode number. So if you see like if you were to see something like in waveguides and it's like TE10, that's not TE10, that's TE10 if it whenever it pops up. Um, so that's an important thing to make sure you note because if you think it's 10 and then it's not 10, things are a lot different. Um, So M and M are indicating the mode number. The electric field is transverse to direction of propagation, and magnetic fields components can exist in the direction of propagation. The magnetic field transverse to direction. I think it's supposed to say perpendicular to direction of propagation. Oh, no, never mind. It is supposed to say the same thing. Electric field has longitudinal components. I'm going to rewrite that just so that way it's a little bit clearer. The electric fields have longitudinal components. Um, and the dominant mode is the largest frequency or the lowest frequency mode for a rectangular waveguide. So, if as you can see here, we drew a rectangular waveguide right here. Um, so a waveguide supports many different modes. Let me see what's the haps. Okay, Bree said she'll pop in, so she'll be here soon. But a waveguide supports many different modes, and these are different solutions to the boundary conditions for E and M. So if you have E tangent, so you look, if you look here, this is the way that the waves are propagating. They may be electric, they may be magnetic, but these are the way the waves are propagating. So you see that the tangent, there's no tangent, and there's a, I think that's what say H normal. I'm telling you, bro. Sometimes I'm telling you, our professor is amazing, but man, he be working fast sometimes. This was like at the end of the year. We barely had any time to write anything at all. So he was trying to make sure we learned this stuff. Um, but the note, you, you, I mean, just assume this. Just assume that these are all solutions to the waveguide. And there's infinitely many modes. So you see there's a T010, there's a TE01, TE11, TM12, TM21, and TEMN or TMNN. It determines the number of half waves in a dimension. And M determines the number of half waves in the oh, excuse me. M determines the number of half waves in a dimension, or in I think that might be X dimension or A dimension. A as in the letter A. And then N determines the number of half waves in the B dimension. So that's another thing. Um, sorry, I had to handle something right there. And also, contrary to what typically happens in general, cutoff for waveguides is the minimum frequency, not the maximum frequency. It's the minimum frequency. So in tradition, most of the time you'll have a cutoff frequency. It'll be like the maximum frequency before something starts to break down, or the cutoff frequency will be where everything starts to resonate, or the cutoff frequency will be like where things start to act properly. In this case, the cutoff frequency is where things start to act properly, but it's the lowest frequency, the minimum frequency that you can have for a waveguide. So that's the difference between waveguides and other things. Um, so how would you find the wavelengths? So just to throw out an equation right there, if you're trying to find the wavelength, the cutoff wavelength, you need to have M, A, and B, M, N, A, and B. So just for as an example, let's make up a waveguide cutoff frequency problem. Let's say our M equals 2, N equals 1, A is 15 millimeters, and B is 25 millimeters. This is not a conventional waveguide. This is just something to visualize what's going on here. So if we were trying to find the cutoff wavelength of this, we would do lambda C equals 1 over the square root of, and I don't ask me why it seems like every time in every engineering class there's 500 billion things under a square root that's squared, that's then square rooted, then divided by it, then square rooted that, and then divide by that, and then multiply by the square of the square root of the minimum. Like, I don't know. It bothers me sometimes. Like, it's just an equation, but it bothers me sometimes. But anyway, I digress. So we're going to take the square root of m over 2a, that gets squared, and then you add that with n over 2b, and that gets squared. So with our handy dandy TI-84 hashtag not sponsor because TI doesn't want to sponsor you, boy, or hire him. Look, TI, if y'all hire me, I promise y'all gonna have the best, biggest, most enthusiastic sponsorship. Um, man, I gotta handle something for my job after the stream. But anyway, TI, if y'all want the best shout out for your products, I mean, I trust your products anyway. I do trust the products. TI is a great product. Um, but if you want the best shout out, get your boy a job. I got you. So we'll plug in the values. Let me zoom in a little bit for those who are like me who have a little bit of hard time seeing things sometimes. So we'll go ahead and take this and we'll do this equals 1 over the square root of 2 over 5 over 30 millimeters. And it's important to know what your units are, because if your units are off, then you'll have an incorrect answer, and that's squared, and that's plus 25. Wait, hold up, excuse me, I'm sorry. That's plus 1 over 25 times 2, so 50 millimeters, and that's squared as well. So we should be able to find the cutoff wavelength with this. And I have a calculator built. I have a calculator that I created on Excel to double check us. So let's see if we get the same answer. Um, so let's do 2 divided by 0.030, then square that, and then do 1 divided by 0.050, then square that. Um, yeah, so square those two, add that to, wait, did I do this right? Oh, yes, yes, I did. Because I'm dividing by a larger number. Okay, yeah, yeah. So that plus this, and then do the square root of that, then 1 over that. So our cutoff wavelength should be about 14.4 millimeters. Now I'm gonna go ahead and go to my Excel calculator that I created for this. Give me just a second to pull it up. Also, the Excel calculator, you can make it yourself. I don't want to share how I made it because it comes from equations that were given to me in a what I'm assuming is a um, um it was pre-love 7. Um, errors detected, no repairs are necessary. Is it pre-lab 6? Um, this one. Okay, cool, 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 cool. Let me just go ahead and save this real quick. I forgot to save it. I don't know why I forgot to save it. I don't know how I forgot to save it, but I know I thought I saved it because I submitted something. Um, yeah, let me just go ahead and save that. Um, so let me go ahead and share this with y'all. But like I was saying, I don't want to show y'all how I made it because it comes from my professor's pre-lab documents, and I don't want to copyright infringe on him. I need to get permission before I share it with anybody. So please have grace with me. I don't want to step on anybody's proverbial toes. Um, but essentially, here's how this works. So like I was saying, our A is 30 millimeters. So if we do 30 millimeters, or no, our A is 15 millimeters. Our B is 25 millimeters. Our M is 2. Our N is 1. Our cutoff wavelength ends up being, what do we get? 14.4. You see how that's the same? That's our cutoff wavelength right here. Exactly the same. So with that equation, you've done it successfully. That we've proven that that equation works. Um, so yeah, so now we can now move on. Um, I just wanted y'all to see that. I just wanted y'all to see that. So um, wavelength of operating frequency. So let me clean this up so y'all can read it. So the wavelength of operating frequency must be shorter than lambda c. That's basically to say that the operating frequency must be larger than the cutoff frequency of the dimension a times b, um, or a and b for the mode mn. So like for this te, the cutoff frequency is the velocity. Velocity equals c. So you do c over wavelength, um, and you end up getting what was it like? Two? I forgot what this was. I don't know. Um, but that should be 1 over 2 A and B. That's just not very clean. So I'm going to clean it up as well again. Um, yeah, I really scribbled this because like this math doesn't even make sense. So in this case where it's TE10, this would actually go to 0 because you have a 0 over a value. So you're really just doing 1 over the square root of 2A squared. Um, so let me just clean this up a little bit. So you have 1 over the square root of 2A squared, 1 over the square root of 1 over 2A squared, excuse me. Well, if you're squaring that, then the square root deletes itself. So you now have 1 over 1 over 2A. When you do that, you have multiplying by the reciprocal. So you just multiply and you just have 2A, 2A. And that just gives you 2A. Wham, bam, thank you, ma'am. So that's what that was supposed to say initially. Um, so I just wanted to make sure that y'all got a chance to see that because it's very important to know where this stuff comes from, because if you don't know where the stuff comes from, you're just going to be lost looking for answers, and I don't want to be lost looking for answers while I'm taking the test. So I need to know where the stuff is coming from. So this is a real waveguide. So find the cutoff frequency for a WR90 waveguide with an A of 22.8 millimeters and a B of 10.16 millimeters. Um, So FC, as you can see, you got C over wavelength C, or you can multiply that by this value, um, multiply the speed of light by this value because you have 1 over 1 over. Um, and just like I explained before, you multiply by the reciprocal. So assuming, I believe, yes, assuming that you have a TE 01 or 10. So if you do this with 10, you can find the cutoff frequency for that. So let me just this is just for practice purposes. So I can get better at doing this. But if we have the speed of light multiplied by the square root of 1 over 2A squared plus 0. Well, let's just do the quick maths. You know, the tinkle script, you know, that song. 2 plus 2 is 4 minus 1, that's 3. Quick maths. Well, quick maths is 2 times 0.22 0.228. Yeah, 0.228. And I'm going to rewrite this so it's actually clearer. So 0.228. Wait, no, 0.0228. 1 divided by that. Square it, square root that, then multiply by C. Sorry, y'all. Excuse me. Excuse me. Um, so you end up getting, let's see, let's count the zeros, um, or count the spaces for scientific notation. So you got 3, 6, 9. So you end up having 6.5.579 times 10 to the ninth hertz. Or right here, should be 5.8. So 6.58 gigahertz. Giga is to the 10 to the ninth, so that's that there. If you do the same thing for TE1 01, well, you'd find. So let's just do this in the other equation. I'm not going to do all four of them. I'm just going to do the first two, because it's the same process regardless of what you're doing. So let's do c times square root of 0 plus 1 over 2 times 10.16 millimeters. I'm trying to figure out like who's sending me messages and stuff like that. Okay. Um, I'm just trying to make it at this point, y'all. This stuff is it's fun while you're not being tested on it, but when you're getting tested on it, it's like pray for me, y'all. Just pray for me, y'all. Anyway, and then this should be squared. I can't forget that square. That square is very important. The square will give you the right answer. Not squaring it will give you the wrong answer. So let's do 10 times 0.01016, 1 over that. Then you do the square of that, square root that. Oh, um, just act like I didn't just do a redundant math step because you should do it that way all the time anyway. Because you won't always it won't always be zero. Sometimes it'll be plus like some other value, and it's not going to always be zero. So multiply that by the value of c, and that oh geez, that gives you a 14.76 gigahertz, and you can see that on the other side. So that gives you 1.476 times 10 to the 10th, or 14.76. I don't like how that 4 looks, so I'm going to rewrite it. So you see how there's different waves, and then if you're going to construct a diagram, you want to have it in between these two values. And in general, as a general rule of thumb, you want to use 25%, if I'm not mistaken, 25% of the two modes that you're trying to work between. So like for the 0 1 mode, or for the yeah, for the 0 1 for the 1 0 mode, goodness gracious, I'm getting all these numbers confused with each other. So if I do 6.58 times 0.25, and then I add that to 6.58, that gives me 8.225. And then if I do 14.76, so 14.76 times 0.25, and then do 14.76 minus that, gives me like 11.07. Um, but that doesn't, I mean, like that works, but also that's not the next highest mode. I just did something incorrectly. The next highest mode is actually 13.16. So 13.16 times 0.25, and then 13.16 minus that gives you like 9.87. Um, wait. Hold up. 12.4. What is that divided by 13.16? That's like 5% off. I don't know how to do the next one. Um, maybe that's 6.78 times 0.75. Yeah, that then plus 6.78. No, that's still 11.8. Um, just as a rule of thumb, just use 25%. Use 25%, you'll probably be fine. Um, and if it's not that, then they'll give it to you like they'll say like the cutoff, the frequencies to use are between these two to stay in this mode. Um, maybe when Bree hops on or James or somebody hops on, we can ask them and double check. But as a rule of thumb, just use 25%. So the next thing, waveguides continue. So if you're wondering what a waveguide does, this is what waveguides do. The direction of the signal, oh geez, the direction of the signal forms an angle with the axis of the waveguide. So sine theta equals lambda over lambda c. If lambda is too close to lambda c, you'll end up having a 90-degree angle. So you don't want a 90-degree angle because that means it's just going up and down, up and down, up and down, up and down, up and down. You want it to have, a pretty good angle. I mean, like, think of it like you're a sniper. You would never, as a sniper, shoot straight up in the air at a 90-degree angle from your position on the ground. If you're shooting at a target over 100 meters away, you're never going to shoot 90 degrees directly at the target. You might aim up a little bit because in general, a lot of things have a parabolic arc, but that's not really what we're dealing with. But you're shooting at some angle to reflect off, assuming that the parabola is a solid substance that you're reflecting off of to hit your target dead on. So you're never aiming directly at something. If you're going to ricochet, you're going to want to ricochet at like a dull angle, I guess. I mean, not a sharp angle, but like a dull angle. You want to like bing bing like that. So guide wavelength needs to be greater than lambda because the wave does not travel in a straight line. So the guide wavelength you can find with lambda over 1 minus lambda over lambda c. Um, so you just take the for an air-filled one, you just take lambda equals the speed of light divided by the operating frequency. Um, the other thing that goes along with this is, wait, hold on, let me make sure. Okay, so let's see. So as you can see here with the range of operating frequencies, this 8.2 and 12.4. Let me see if I can find this on Google or something like that, like how to find the top edge of operating. Low battery. Oh,
Aren't you plugged in?
I thought I had a full charge. Um, I know my phone didn't have a full charge. That's why I didn't plug. That's why my phone's plugged in. But I thought my iPad had a full charge, and then it tells me I'm at 10%. Um, Also, if you see me like rubbing my face like this, I'm not. It's not me scratching my face. My mustache is coming in, so like it's kind of fun to play with. Um. Anyway, how to find top or yeah, no, how to find upper limit of operating frequency on or of wave guide. Google told me the operation frequency is 125% to 190% of the cutoff frequency. Okay, so if I multiply 6.78 times 0.9 and then add that to 6.78. Oh, okay, okay. So it says 125% to 190%. That's close enough. We don't want it that close to 13, so we're gonna bring it down just a shim. But that makes sense. So if we're gonna find the operating range of frequencies or the operating range of a WR90 waveguide, what we need to do is, am I even on the right page on my thing? I am not. What we need to do is take the 8.2 gigahertz and the 12.4 gigahertz and find the wavelengths that it takes to get there. So the way we find wavelengths is we take frequency, speed of light over frequency. So we take the speed of light. Oh heavens! Um, take the speed of light, which is c, divide that by our frequency, so 8.4 for the low end, and then we take our speed of light and divide that by frequency at the high end, which is 12 point. Wait, no, it's 8.2 and 12.4. Put our units there. Okay, so if we do that, do alpha C. I'm telling you, man, get you a TI-84. These things, they make my life so much easier once you figure out how to use them. That's the disclaimer I'll give you. Once you figure out how to use, you got to figure out how to use them first. But anyway, so alpha C divided by 8.2 times 10 to the 9th. That gives you 36 centimeters, as we have written down here, but we're going to rewrite it. So 36.59 centimeters. And then we do the same thing again with 12.4 gigahertz. So we have alpha C divided by 12.4 to the negative, or not negative, to the 9th. And then we get 24.2 centimeters, or I guess we'll say 19. So 24.19 centimeters. And then we can find the guide wavelength from this equation. Um, oh, okay. So um, our cutoff frequency for this was oh geez, I think it was like 6.78 gigahertz. So cutoff frequency or lambda cutoff or cutoff frequency, excuse me. Yeah, cutoff frequency is 6.78 gigahertz. So if we do the speed of light divided by that, so alpha C divided by 6.78 times 10 to the 9th, you get 44 44 centimeters. Let me just, jeez. I can do this way, right? Hold on. Let me see if I can do this way. 8.2 divided by 1.5. Oh, wait, no, not 7858, 6.58. That's a big, big difference. 6.58 to 7.8 is a huge difference when you're dealing with gigahertz. Okay, so I think it's 45 centimeters. Yeah, so lambda C is 45.5. Well, I guess it would be 6. 45.6 centimeters. Um, so then we can use our equation here. So to find the guide wavelength, we'd say gamma G, or lambda G equals the original. So that's 40. Wait, no. So lambda G of 8.2 is 8.2 gigahertz, or not that. That would be 36.59 centimeters divided by um the square root. Yes, square root of 1 minus 36.59 centimeters over 45.6 centimeters. That value squared. And then that should give us the same value that I calculated earlier in the class. That value squared, 1 minus that value, square root that, and then do 36.59 divided by that. So our guide wavelength, like as it should be, is longer. Um, and we ended up getting 61.31, 61.31 centimeters. So that's how that ended up working out. Let me just check the chat, see if anybody said anything. Um, yo, what's good, man? What's good, Richard? Um, so yeah, so that's the 8.2 gigahertz. For the 12.4 gigahertz, it's a very similar process. So lambda G equals 20 24.19. I'm gonna start doing these study streams like throughout the whole semester. One, it'll get me to study like more, so I'll do better in my classes inherently because I'll be studying more. But also, apparently, y'all like seeing me do engineering stuff. I kind of wanted to do engineering stuff on my YouTube channel, but I didn't think that I would be able to do it with regular classes. But I mean, it seems like y'all enjoy it, so y'all have opened my eyes to see that engineering stuff is another thing I can do on here. Now I don't have to choose between studying and live streaming. I can do both. About to reach 4 million subscribers just from studying on YouTube. This is, by the way, I want to make this very clear. This is not a substitute for college. This is not a substitute for higher education. Don't watch my videos and my live streams and learn how to do waveguides and stuff like that, and then think you can go work for NASA. No, this is not a substitute. This is to help me and anyone else who has to take the classes or classes similar to what I take study. Okay. Okay. You're not an engineer. You're just some dude watching some engineering student try to study for his exams. Okay. Okay. Cool. Cool. Awesome. I had to put that disclaimer out there because there's some Yahoo out there that's gonna think, oh, I watched a Kristen Ninja live stream one time about how waveguides work, and I could go work for NASA. Like, no, no, you couldn't. You could not work for NASA right now after watching one video from me. You think 1 hour of education adds up to everything in college? Maybe 4.5 hours of education could add up to. No, I'm just kidding. I'm just kidding. But for real though, do not take this as a substitute for college. This is not a substitute. This is to help study. Okay. All right. Cool. Glad we understand each other. Okay. I think I should have 28 centimeters. And yeah, that's exactly what we got. So now we move over here. Now I can explain phase velocity. That's what I was trying to explain before, but I didn't want to jump the gun, and then y'all not really understand what's going on here. So the speed on which the constant phase front makes down the waveguide. Um, I don't really understand what that means in general as a concept, but essentially that's saying like I don't understand like the wording in this context, but if I had to explain it to you, um, like shout out Tyree, my little brother. If I had to explain it to my little brother, basically a phase velocity is there's something leading your signal, and in order to be ahead of something, you have to be faster than it. So being faster than that signal just means that you're moving quicker than that means you're ahead, and that's the phase velocity. That's the a phase shift. When I'm ahead of you, I'm out of phase with you. When we're running together, we're in phase, we're in sync. When we're out of phase, one of us is leading the other and one of us is lagging the other. So that's how it ends up working. So phase velocity is the guide wavelength multiplied by a frequency. This can be faster than the speed of light. Okay, that's very important for you to know. They say nothing is faster than the speed of light. That's a lie. Phase velocity can be faster than the speed of light. Okay. Okay. Cool. So, um, what is this value? Oh my cheese and crackers. Um, so it looks like the velocity of the guide velocity can also be found with the speed of light times cosine theta, which is also the speed of light times lambda over lambda g or guide lambda. Can also be found with with c squared divided by the velocity of propagation. Vp is a c over 1 minus c over the square root of 1 minus lambda over lambda c squared. Excuse me. Um, or c over the square root of 1 minus fc over f squared. Okay, cool, cool. Love it. Love to see it. Um, Waveguide, you could just say C times square root of one minus uh the lambda over lambda c squared, or C times square root of one minus FC over F squared. Um, so that's how that works. So example, find the phase and group velocity. Oh, that's what it stands for. Group velocity, not G velocity, group velocity. Find the phase and group velocities of a wave propagating at 8.2 gigahertz. Um, so uh oh, we didn't solve it. He just gave us the answers because we were trying to work fast. So gotta stretch out for this one. Hold up, y'all. Gotta stretch. About to make a big mind play. We're using a big mind play right here. Okay. So this is actually where I got to teach myself something real quick. All right, now. So we know that the phase velocity is this equation. We know the phase velocity is this equation over here on the left-hand side of the screen. So I'm going to write that in purple so I don't get confused with the original notes, and you don't think that I wrote that with stuff. So you have C over. Oh, that's really big. That's really big. Zoom in just a tad bit. You have a C over the square root of one minus lambda. I think that's lambda over lambda C. Yeah, lambda over lambda C, and that's squared. So we know what the cutoff lambda is for this WR190 waveguide. We know what that cutoff is. Because we've been using it. I forgot what it was, but 45.6 centimeters. So we do C over the square root of 1 minus 45.6, 40, geez, 45.6 centimeters divided by, oh, wait, no, wait, hold up. My bad. Writing the wrong values. Sorry, y'all. This is exactly what I said. This is not a college course. This is not equivalent to a college course. You think the professors make mistakes? I make mistakes. Like, come on now. I need 36.59 centimeters. Okay, yeah, yeah. And that's divided by 45.6 centimeters, and that value squared. Okay, so now that we have the right values, we can do that's not right. Okay, that's right. And then divide that by 45.6. Okay, yeah, yeah. Mm, wait a second. Wait a second. I've been saying this wrong the whole time. I'm gonna have to ask y'all to call. I'm gonna have to ask y'all to forgive me. I've been saying this wrong the whole time. I should have just stuck with millimeters. My goofy self. I should have just stuck with millimeters. All these centimeter values, they should be millimeters. I'm sorry. Um, that will give you a wrong answer on tests and stuff like that. You just follow engineering notation. It's so much easier to remember. Just follow engineering notation. -3, -6, -9, -12. And then just take negatives apart for everything else. Like just geez, man. The num the math is correct. The numbers are just off by a factor of 10. Anyway, okay, square that value. Second square root that. Oh wait, hold on. No. Square that value. Then 1 minus this. Then square root that value. And then do the speed of light. So with that, if we remember, the speed of light is 3 times 10 to the eighth meters per second. And we move this over 1, 2, 3, 4, 5, 6, 7, 8. So now we have VP. That's what it equals. So to get really technical, be 5.02 or 5.03, excuse me. This is closer to the actual value, but 5 will work just fine. Just gonna check the chat real quick. Okay, we're good. Um, okay, cool. It's hard trying to manage like 5 different things at once, but this is all for the betterment of my studies. Um, and then we can do the same thing except we do c times that, and that gives us our group velocity. So if we do, oh geez, if we do alpha c times this value, which is the same thing. Wait, yes, it is the same thing. Um, that gives us, I think, 1.7. Oh, wait, yes, it does. Yes, it does. 1.790. 3 times 10 to the eighth. Then you do the same thing for 12.4 gigahertz, and that gives you your thing. For impedance, B equals IR, B equals IZ. Same thing as you've been seeing 1,000 times before. Um, in waveguides fields vary in both directions. So there's no characteristic impedance. Um, so you can say that Z omega lambda. I don't know. Just you. How can I explain this? So you have your value nu. Nu is I think it's 377 ohms. Um, and you just multiply that by one minus the lambda over the mode you're in squared. When f is much greater, that's what these two inequality signs mean. When f is much greater than fc, then z naught is roughly 377. Um, so that's how that really works. But yeah, so you can do it that way. Losses in rectangular waveguides. You have your attenuation at cutoff, which is alpha 8.656 or 8.686, excuse me, 8.686. Then you multiply that by the cutoff frequency, divide that by the operating frequency, square it minus one. That gives you the dB per meter. Um, if F is greater than FC, dissipative losses and conductive wave. So you have your mode. That's 4.4578 times 10 to the minus 5. And then that's times the operating frequency over sigma, which is usually skin depth. Then you do 1 over B, and then all this lovely, beautiful, very much hated math. I think this is 2B over A. Then F FC over F squared, uh, square root of that 1 minus FC over F squared. For this particular waveguide that we've been working with, that attenuation is 0.199 decibels per meter. Um, at 5 gigahertz, uh, yeah, so I didn't draw circular waveguides on here, I don't think. So, oh no, I did. Circular waveguides, they have the same modes, except that it's 2 pi r over p prime for TE modes, and then lambda cutoff of mm is 2 pi r over p mn. You see. Let me zoom in for y'all. So for TE modes and TM modes, it's different. Um, the fields, the fields inside the cylindrical structures are governed by Bessel function. Jeez, all these people got named like functions named after them. When am I gonna get my shot, man? The Chris function, the ninja function. Like, who's Bessel? But the roots are in the table. Um, find the cutoff frequency of the circuit waveguide. You need to use a table for this. There's a table I didn't put in here, but like yeah, you can find that. If you just look up the Bessel functions. Antennas. Let's see, we've been on for wow. Oh wow, you've only been on for an hour. That's not too bad. Um, So you probably know what an antenna is. You probably don't know how it works. I mean that in no demeaning way. Most people don't even know how antennas work. I was talking to my professor. He was like, he still doesn't understand how all this stuff works as a whole. He's still figuring it out. Um, and this dude's been doing this for like 20 years, man. Master of electrical engineering, professor for like 10 or 15 years or something like that. This man still trying to figure it out. What chance do I have? Pretty darn good chance if I do say so myself. I could probably figure it out eventually. Give me like 25 years and lose all my hair and start teaching electromagnetism. Um, but antennas work at a specific frequency, so you shouldn't be having antennas that can read. Oh, actually, you know what? This is a great time to show y'all what we built in class. So this right here is an antenna that we built in class. We built. Let me stop sharing for a moment. Y'all can really see it. This is an antenna we built in class right here. This is the one we built. It works at 90.9 megahertz. It works at a very specific frequency, and with it working at that frequency, we can't get really anything else out of it. Like we can't really get any other. Can't get really anything else out. Oh yeah, Bree's showing hers off as well. Um, Bree, what was your frequency at?
We matched ours to 104.7
So
and it worked.
notice how. Go ahead.
I expect the things out. They're really long. They're all good together. But yeah, this is our antenna. A better visual of what it is. Yeah, thought I would share.
But yeah, I was just gonna say, if you notice, both of our antennas are not the same. Hers is a little bit, I think it's a little bit longer on the um the arms. And I think hers is a little bit taller as well. But that's because they're matched to different frequencies. So back to the back to the cool stuff. It's not so cool because I'm stressed, bro. It's gonna be okay. It's gonna be okay. Um, Also, hold up. I gotta shout myself out real quick. Look at this circle right here, man. Look at this sphere. This sphere almost looks professional. I just gotta shout myself out real quick. Okay, back to the real stuff. Bro, I swear. What do these people want? Watch it be James. It was James. Okay. Anyway, so antennas act as a boundary condition and form uh a distribution. Golly, man. I wish he taught like 20% slower so I could actually take the time to write this stuff neatly. Form a distribution. You see how much you s- just wait like 3 seconds when it pops up. See how much nicer it looks. You're gonna see it. You're gonna see how much nicer it looks when I have the time to write stuff. This is how much nicer my writing can be. Um, as current has changed. So this says definition, and this says Duradian. Um, so how can I put this? So essentially, a steradian. I gotta go. Gotta go back to geometry. Like how Eminem snaps back to reality. I gotta snap back to geometry. So snapping back to geometry, if you look here, you have a circle, and there's some value where there's an angle, and you're trying to find that length right there. So you take theta and you divide that by 2 pi, and you multiply that by I think that's by the circumference. Um, so that's theta times, golly, man, 2 pi, jeez, 3, dang it, crap, 2 pi r. Um, so that's how you find that arc length right there. Well, steradian is like a circle on a sphere because a sphere is just a giant 3D circle. If you were to take a circle and spin it, really, really, I'm not going to go up. I'm not going to get up and get a coin, but if just as an experiment, just to show you what I mean, take a coin, spin it on your desk. See how it looks like a sphere? That's what we're making the point of. So the uh, there's miniature circles all over the sphere. The surface area is 4 pi r squared, and there are 4 pi steradians patterns with an area of r squared in the surface of the sphere. This is a measure. This is a measurement of how of the solid angle, solid angle. I hope that's what that says. I really hope that's what that says. Um, let's see. So power density. Oh, where is that equation? Where is that equation? Where is that equation? This is an equation that you're gonna want to remember. Like for sure, for sure. I don't remember where it is. I know I wrote it down. I know I scribbled it down. Let's see, let's see. I know I scribbled it down somewhere. I know I scribbled it down. It was something that threw me for a loop on the last exam. I think I remember it was in this right here. It should be somewhere like way over here. I'm trying to find it because like it was something that was chewing me up and spitting me out last exam. Bree, do you have a power density equation written down? So I'm trying to find it so I can write it down again. The original power density equation. It was in one of these. It was in one of these. It was in one of these. I don't know what it was. Okay, here it is. Here it is. Here it is. Oh my god, found it. Found it. Okay. Um. um so you can find the total power density. This is just like for us ESET 355 nerds for the most part. Got to snag all of this. Bro, I should be a teacher for real. Like Oh, that's quite large. Okay. Okay, cool. See, this is the stuff. This is the stuff right here. This is it. Just make that a little bit smaller. Okay, so power density. Um, I don't know why I started talking about power density. I forgot. But power density, you can find it with gamma squared multiplied by EI times HI. That's initial. That gives you the initial power. So if you do P initial, and then you multiply that by 1 minus gamma squared, that gives you P total. If you were to divide P total by 1 minus gamma squared, that gives you P initial. So if that pops up on the 355 final, if you were here in the live stream, Krista Ninja got you covered. I got y'all for sure, for sure, for sure, for sure. Okay. Anyway, back to the study. I just had to find that because I was gonna completely forget, and then we would have been. Oh, that's why I did this. So power density, the amount of power of watts per area of the amount of power per unit area. So that ends up being volts per meter, and that's volts per meter squared. So it's volts per meter times amps per meter, volts per meter squared. That's the same thing as this over here. That's pretty much all this is. So you see how this is ER times HR, and this is E times H. That's the same thing. Basically, yeah. Go ahead, Granddad. Question.
Yeah, is there different power density? I was looking at it was saying that it was saying it was the output power processed by the system. Then it had volt knot times volt knot, and then it said divided by the regular area, which L times W. So is that a different power density?
I believe that's a different way to represent power density. In the way that we're trying to represent it, we're representing it as signals, so
Uh-huh,
electromagnetic waves and stuff like that.
uh-huh.
Um, so in general, power is measured in watts. Does the thing you just looked up give it to you in watts as
Oh,
the final unit?
no, it doesn't say. Let me take.
So power is usually measured in watts. With your light bulbs and stuff like that, you have a 40 watt, 80 watt bulb and stuff like that.
Uh,
Um, and watts is just volts times amps. Um, and that gives you, yeah,
but it
yeah.
says the power density is at P times G divide over 4 times pi times D2.
Oh, that's something that's over here. That's something over here. Something like this. I'll get there in a moment. But oh geez, what did I just do?
I just saw that and I was just asking if go ahead and do what you're doing. Go ahead.
Um, to explain. Oh geez, this is.
No, didn't want to distract you. I just thought I would ask
Oh,
you.
oh no, I thought I had to
Go ahead
sneeze.
and keep on with what you're doing.
Well, the reason I'm going to explain it like kind of briefly now is because it helps to know what you're doing. So
Okay.
power density, like I was saying, it can be measured in different ways or it can be represented in different ways.
Hmm.
Much like how voltage can be represented as a potential difference, it can be represented as a electricity. It can be represented as a wave form. Like there's multiple ways to represent voltage, but it all points to the same thing. For this application, our power density is representing different electromagnetic waves. And when you have a wave propagating through a coaxial cable or an antenna or something like that, it will have to it will create a potential difference, which is a voltage, and it has to have a current to flow through, and that creates power. And you're trying to find how much power is over a certain amount of area. So if the power is like 2 watts per meter, that's quite a bit of power going through that. But if it's like 5 microwatts per meter, that's not as much power. So that's where power density comes in, and it's always measured in watts. So as long as you're getting watts, you're on the right track. So I hope that answers the question somewhat. Good question. So essentially, the way that this works is that there's a it forms it forms EM waves when you put it on a on an antenna. So some of it goes this way, and then that makes it like loop this way, and then it'll reverse and it goes this way, and yeah. And essentially, what happens is you have some waves propagating out like this, and you have some waves propagating out like this, and then they get all the way out, and you just have a circle. You have what looks like a circular waveform, and then that warps. Let me see if I can find it real quick. Uh, from Dr. Bosshard's slideshow. So just gonna share this real quick. So if you look at this image right here, you can see how the waves kind of warp as they move further away. But when you look really carefully, you can see that they started out essentially as circles and they've been pushed to be warped. I don't know if y'all can see. Like, can you see that? I hope y'all can see that. Um,
I
people in
can,
the stream, people on the so like it starts out kind of circular and then it propagates out and gets more and more warped. This is another representation of the radiation pattern. I'm not trying to share too much of I'm not trying to share too much of his stuff because I'm not trying to violate his copyright violation, his copyright, everything like that. But I just wanted to show y'all like what it looks like. Those are images that were pulled from the internet, so I'm hoping he doesn't mind that I showed how those waves propagate um, for illustrative purposes, education and all that. Oh my goodness! Everything almost fell apart right there. I would have had to end the live stream. Everything almost fell apart. I just got a message from Bree saying her computer had died, so she'll be back soon. But anyway, oh goodness, I'm about to drop my iPad. Okay, so let's see. Um, so we got through that. We got through that. So we want to find the far. So if so, we're trying to find like a few different things when it comes to antennas. Far field is one of them. To like the received far field resistance or whatever you want to call it. And that's defined as 2D squared over lambda. Um, D is the dimension of the antenna. Um, you can also, I think there's also far field. I think you can define it as lambda over 2 as well. But just use this equation and as a fail safe. So Granddad, do you pick a dimension? We're gonna do a quick far field problem. So pick a few numbers for us. Pick a dimension, like pick a size for dimension.
pick a size for dimension. Say,
Hmm.
what are we looking at a particular shape or something like this, or just
We're looking at an antenna, so give me a size for an antenna. How big do you want the antenna to be?
well, let's say we want to be 100 watts.
No, how big? Like the size of it.
Okay, the size of it, let's say for the width of it, well, let's say the width be about 36, be of 1 meter.
Okay, well let's give it 11 meters. Okay, we'll say 11 meters. That way we have like
Okay,
that way it's
that's
not just like
big.
one over something.
Okay.
So we have 11 meter, we have an 11-meter antenna. And we'll just say it's operating at a frequency of what's your favorite radio station?
Well, 104.1.
We'll say 104.1. Shout out to Virginia natives. Y'all, if y'all know, or specifically northern or like I guess central Virginia, northern Virginia natives,
Yeah.
y'all know that channel. Y'all should know that channel. So 104.1 megahertz. So we know that the velocity of the propagating wave is the speed of light. So we do C over 104.1 megahertz. That gives us a wavelength of 2.8 meters. 2.88 meters. And then we have 11 squared. That's multiplied by 2. And then divide that by the lambda we just found. And that gives us an RFF. So to write this out, 11 meters squared times 2 divided by 2.88 meters. And that equals 83.97 meters. If we do lambda over 2, trying to see how this works. Oh, y'all can't even see it. There we go. Here's the numbers.
Okay.
I'm trying to see how this works out exactly. 2 times lambda over 2 squared lambda. 2 times lambda squared over 4 over lambda. This becomes lambda 2. Oh, no, that becomes lambda squared over 2. Okay, so this math that I just did here proves that this is equal to this. Um, so I don't know exactly where this comes from. Like I don't know exactly what this lambda over 2 thing is. Um, let me try and solve it. Wait, hold up. Over square that, then multiply by 2, and divide by I think these are two different things. But in far field waves, they behave mostly like plane waves. Um, I'm gonna assume that these are two different things. Because I get two very, very different values. Two very, very different values. I'll collaborate with my group mates and stuff like that later and ensure the correct formula because I want to make sure we got the right stuff.
That's good.
But yeah. So that's how we do that problem. Radiation frequency is theoretical. It's basically it can radiate in a circle, but we know that doesn't happen. Or it can radiate in a sphere, but we know that doesn't happen. So we can find power density with the power transmitted divided by 4 pi r squared. That gives you watts per meter squared. Radiation intensity is r squared times the power density. So it's r squared times r squared, or no, it's it's this. So it's r squared times this. Power radiated per seradian. Um, so U is 50 watts per seradian for an additional for an antenna field. P at 25 kilometers. So you do 50 watts over, or I guess it's 2.5, no, 25 kilometers. You do that, and then you end up having 0.8 microwatts per meter squared.
Okay, that now that U represents, you said that's 50.
U represents um, the radiation intensity.
Okay, okay.
So let me write that a little bit more clearly.
What does the term U stand for?
I don't really know. I just know it represents radiation intensity.
Okay, that's good.
Um, so yeah, if you do 50 divided by that, you get 0.8 microwatts per meter. If we know how far the wave is from the transmitter and we know how the effective area, we can find the time to receive power. And that's all I have written for this one. So we have radiation patterns. Um, so most times you'll end up having lobes because we can only radiate in a direction. The principal plane pattern, often radiation pattern, is plotted in 2D or on 2D planes. So the E plane containing electric field vector on the main lobe above the 2D pattern. So U and dB, the radiation intensity in dB is U value divided by U naught, which is the max value here, 10 log of that. In actuality, we want it to be kind of off. So this is like extreme asymmetric finite waves and the connectivity coupling, but most of the energy comes out of the main lobe. Um, Once again, on isotropic antennas, that's omnidirectional. It's doesn't exist. Um, the lobe can have a few different bandwidths with different patterns, and you can find U naught with the power radiated divided by 4 pi. and that's the power radiated per seradian. So I guess in a way it's a way to represent power in seradians rather than watts. Um, so yeah, if we wanted, so like as an example, just to let's just say that U, our original U, switch pages real quick. Let's say that we have U equals 25 watts, and then U naught is 0.3. Wait, no, I guess max would be higher. We'd have 150 watts per seradian. So to find the U and dB, you would do 10 log of 25 over 150. And that gives you minus 7.7 dB. Um, to find U naught, so let's say that so since we said U naught is 150, if we multiply 150 by 4 pi, that tells us our power radiated is 1.8 kilowatts. So we can find power radiated that way. Yeah, 4 power squared.
When you multiply that time 4 pi, then you have to go back to defining the value of pi, and then you multiply that times 4.
Well, you don't need to find the value of pi. Pi is consistent. So if you just have a calculator that can multiply by pi, you'll be fine.
Yeah, this calculator I got here, except it doesn't have much sense. What was that calculator you were saying, TX?
The TI-84 CE.
Okay, I'm gonna look that up. Okay. Yeah, okay. Go ahead.
Okay. So you can say U is power density times R squared. Essentially what this equation here is saying power density is U times R, or U is power density times R squared. That's essentially what it's saying. Um, directivity, which is directivity is here. Um, radiation intensity of antenna at a non-isotropic antenna. How much better is it at direction? So you can see that here. 4 pi times U over P rad, that gives you the directivity. This tells us how focused an antenna is at a particular direction. And we usually are interested in the main lobe. So directivity, D naught, is U max over P rad over 4 pi, or U max over U naught. And it excludes any losses. P total is PN equals, or PN minus P transmitter. So P rad plus P loss plus P transmitted, or P reflected. That gives you the P total. Antenna efficiency, you do P rad over PN, which is the power radiated over power in, or power radiated over the power transmitted, and that gives you your new value. That's the efficiency. Gain and directivity are typically used interchangeably, even though they're not exactly the same. But you have U over PN over 4 pi, U, and then you just have 4 pi times U max over PN. And then that G log or 10 log of G naught, and that gives you the loss in dB. Let's see. Is there anything else? So here's some practice problems. I don't know if I'm going to do any of them because I've already done them yesterday.
So how did you get in the rest last night?
Yeah, I got plenty of rest last night. I went to bed at like 10,
Oh, you did?
10:30.
That's good. That's good.
Yeah, I got plenty of rest. I couldn't sleep though. I kept waking up in the middle of the night, but I just kept going back to sleep.
Yeah, that's good. That's good. Oh, yeah, that's good to know. Let me see something I wanted to ask you. Oh, what about you ever use you was mentioned earlier that the professor speaks pretty fast and some of the things he have you ever been able to take screenshots sometime of what he has on the board?
Mm. Um, if he's writing too fast or if I miss too much stuff, then I'll take a picture or a screenshot of what he's writing down. But for me, taking screenshots is not effective because I won't look at them later. So I need to write down the notes by hand or else I won't learn from it.
Okay. What about audio?
Audio, I mean, I can understand what he's saying fast enough. It's just a matter of writing it at the same time that makes the writing look very messy and um stuff like that.
Yeah, but what I'm saying is, would it help that after you, even though you write your notes and things, would it help if you went back and listened to a tape of what he said?
I'm not sure. I'm not really worried about it because I understand it well enough in the moments to get it, so I'm not too worried about it.
Okay, that's good. That's good. Just
Oh, okay. So effective area. This is something that I should go over real quick.
Okay.
Let me see. So effective area um can be computed from directivity. So you do lambda squared over 4 pi times directivity. So if we're finding the effective area of a 5 gigahertz antenna, let me before I do this, let me just let Bree know that she can watch back later.
Uh, oh, okay. Okay.
Okay, so geez, my chin itches.
It,
I'm letting James know what I went over.
it,
So what I was saying um was effective area, um, power times it, basically all of this is effective area, but it's easiest calculated depending on on the information you're given. So you could do power times the effective area, or you could well no, power times effective area just tells you how much power. I think that's power density. Um, but effective area can be configured or computed from lambda squared over 4 pi d. So in this example, Then I'm going to scroll down here and full screen it. In this example, you find lambda once again by using the value c, which is speed of light divided by 5 gigahertz. So that's 5 times 10 to the 9th. That gives us 0.06 meters. And just as a rule of, just as a natural rule, you can never, ever, 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 until I learn otherwise, work with dB while it's in decibels. So what you need to do is where did I get 53? What is 53? What I think 15. Let me see. 10 to the nope, that's not right. So 10 to the
And
10.
if you were paying me, I would have got rich.
What do you mean you'd have gotten rich?
If that was dollars, yeah.
No, I would have double checked it before I gave you the money.
Oh, okay. I thought of one thing when you were working this problem. I was looking at that. Now we'll talk. What you're discussing now is sound waves. That's right.
You could think of them that way.
Okay.
I don't mean that in like a demeaning term or like you don't understand. Like sound waves is a way you can think of them because that's also an electromagnetic wave.
Yeah.
Um,
They
there's
just
just
go one direction though, right?
no, they can go any direction. So like right now we're working with directivity. So you know when you would when you get a piece of paper and you or when you get a if you got a piece of paper or one of those bull horns for the football games and stuff like that,
Yeah.
and you yell into it and it directs the sound to one direction,
Uh-huh.
that's directivity, but the people around you can still kind of hear what you're saying.
Oh, okay. Okay.
So that's all directivity is. It's like I'm directing all of my vocal. If I connected my microphone to my laptop, instead of hearing almost a surround sound voice, you would just hear like from my microphone specifically what's coming in and what's going out. You know,
Okay.
that's the main difference. So that's 15 over 10. That gives you 31.6. See, isn't it a good thing that I came back to this and started working it over again?
Yeah.
Got to catch y'all if I'm whacking. So then you take the wavelengths, you square those. So 0.06 wavelengths squared gives you 0.0036 over 4 pi, multiplied by 31.6 using parentheses. And that gives us 9.059 millimeters squared. And then if you move the decimal place over 3 spots, you get the same number as this.
Okay. You square that 0.06. You square that, right?
Yes, because that's lambda. That's the lambda we found.
Okay. All right.
I should define that here.
Oh, I see up the top. That okay, yeah, all right. So
Yes, that's lambda.
okay, all right.
Um, let's see. I didn't write anything on the far side of the screen. Okay, cool. So now we can do polarization, dielectric fields relative to the antenna and Earth. Um, that's basically this. I don't think we'll be tested over this. because
Mm,
there was not really an equation given for this. He might just say like, how is how is the how are dielectric fields polarized? So you see, it's you see that this is perpendicular to the Earth. That's vertical
yeah,
polarization. This is
right.
parallel to the Earth. Um, that's horizontal polarization.
Is
So the
there,
impedance of it, what?
do you have to have, is there a demand whether it should be parallel or perpendicular?
I believe it's both. It depends on what your application is and what the antenna is itself. We didn't really get into it that deeply, so I don't think we'll be really tested over it too much.
Well, far as, okay, that end, that perpendicular, we know that's in the grad goes into, as grounded. Okay,
No,
so
not grounded, but it's in the direction.
you say it's not grounded, that's, well, okay, when you're making that, well, how are you anchored? How are you, but the system still have to be grounded, is that correct?
Yes, in general, it does need to still be grounded.
And is there a measurement how deep the ground would need to be or to solidify, uh, you know, this,
What it's showing is that the signals are coming in vertically in relative to the earth. So it's like you put a pole in the ground.
yeah,
The pole is perpendicular. If
okay,
you lay a pole on the ground, the pole is parallel.
right.
That's all it's saying. We didn't get really deep into it, so I can't really explain it that well.
Oh, okay. That's good.
But if we're looking at antenna impedance, the impedance at the terminals of the antenna, that's the Z impedance. So you take the VN and IN, and that tells you the impedance of the antenna. So Z antenna is usually complex. That means remember 2 or 3 days ago when I was telling you like there's imaginary numbers, you can't add complex numbers and blah 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 all that.
Yeah,
We're back to that again. So you see how all of this is it's all connected, but it seems like different concepts, right?
yeah, you're right. They are changing. Okay.
So it's all connected. They're not all the same, but it's all interconnected. It's all relatively the same, if you will. I'm just gonna check the stream chat to see if anybody said anything. Um, Nobody said anything, so that's all good. Apparently, there. Wait, hold up. I think I'm the second person watching.
It's you.
Uh, am I? Am I? No, I guess I'm not. Cool. I'm not by myself now. Awesome. Oh, well, let's drag this back up. Okay, cool. Um, and also anybody in the chat, I apologize if I don't get to your message. If you leave a message and I don't happen to read it, it's not I don't want to. I just am focusing on something a little bit more important at the moment. But it will be read by the end of the stream, promise. So it's usually complex and it's usually operated uh at or near its resonant frequency.
Okay.
So you can find RRAD by doing the power radiated divided by the current. And the Z naught is R loss. That small R rad is how much power is entering the antenna is radiated, and then that's plus or minus a JX value. Um, so we like I said, he was going really fast at this point, so we didn't get very deep into it. But I guess we could do an example to practice these concepts. Am I even
Chris,
on the right page? What?
is that Z not the same as Zeta?
No, it's not.
It's not okay. I was looking at, that's okay.
So just as an example, let's say we have our P radiated is equal to U, and that's equal to 76 watts. We'll say our current N is 304 milliamps, or 0.304 amps. So we can solve this.
304, you say?
Yeah, 0.304 amps.
Oh, okay. I see it coming up now. Okay.
So if we're going to solve this, we do P rad over IN. So if we do 76 divided by 0.304, we get 250 ohms of resistance for of resistance going into that's power going into the load. So R rad equals 205. I don't remember what R loss is, but let's just say that R loss is like 3 ohms. So R loss is 3 ohms. So you have 3 plus 250. By the way, I didn't have these numbers ahead of time. They just lined up to be nice numbers. So shout out to the Lord for dropping that number in my mind.
Yeah.
And then that's plus or minus like let's say we have do you like capacitors or inductors more, Granddad?
Capacitor since it stores energy.
So let's say we have a capacitor. What's your favorite number?
How low?
Any number. What's your absolute favorite number?
75.
So let's say we have a 75 nanofarad capacitor,
Okay.
and we're operating at how many yards did Jake Browning have last game?
I don't know. I see.
Hey Google,
Oh,
how many yards did Jake Browning have on Monday? So he had 354 passing yards. So we'll use that and we'll make that our frequency. So 354 mega or giga.
let's make it mega.
Megahertz. All right, cool. If y'all on the stream couldn't tell, I'm a kind of a Bengals fan. Just a little
Oh,
bit.
that was your new quarterback you were talking about.
Yeah,
Oh,
yeah,
oh, that's really not even knowing. All I know is Burrow.
yeah. We got 2 JBs on the team. Get Justin Bieber on there, and we'll have a third backup that might throw some yards on there.
No, you don't need him.
Okay, so we can find our complex impedance by doing 1 over omega j c equals z. So just because I forgot how our professor explained it in the review session, but there's actually a scientific explanation why it's always negative. Um, it's because when you're solving for C to get it out of the negative, you have to multiply by J.
Uh-huh.
Or you have to multiply by 1 over J or something like that. And then when you multiply by 1 over J by 1 over blah 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 J, you end up having 1 over J squared, and then J squared is just -1. So it's 1 over -1, and that equals negative. That's just a negative number.
Denise.
I got a question for you.
Yeah, what's up?
Excuse me. Um, is now I'm looking at omega. Omega is also the ohm sign.
So there's just like just like just like just like our alphabet, I couldn't think of the word for a second. Just like our alphabet, the Greek alphabet has capital and lowercase letters.
Yeah. Well, see, I looked at it. You have so the omega sign you use as lowercase.
So angular frequency or angular velocity is
Uh-huh.
lowercase omega,
Okay.
and then capital omega is ohms.
Okay. Okay. All right. Now that makes sense. That makes sense. Okay.
It gets confusing when you're saying
Lowercase is huh?
it gets confusing when you're just saying it, but like if you look over here, this is omega,
Uh-huh.
and then this is supposedly omega. I didn't draw it perfectly, but the two of just for anyone else who may be confused in the future,
Uh-huh.
capital omega, this is just like a quick note. Capital omega looks like this, lowercase omega looks like that whenever it pops up.
Okay. Yeah, okay. That's what I want. That's what I was interested in because I saw it. You know, it looked kind of like a W, but
Yeah, so a lot of people in our classes call it W,
yeah,
and
yeah, I see what
just because me personally, I love the omega symbol, it bothers me, but I can see where they get it.
yeah, I see what it looks. Yeah, you have to look at it close because it's open at the top. It's like two zeros and it's open at the top, you know. Yeah,
Yeah,
okay.
I suppose
And
that's how you. I suppose that's how you can look at it.
and the ohm sign that well see I'd always looked at that as ohm, you know, because of the inventor, right? His last name was Ohms.
Mm-hmm.
Yeah. But the omega, I had to pull that out when I saw the ohm sign. So it's the same thing, but one, okay, I see one is used represent ohms, the other one represent omega. Okay, all right, it works.
Yep. Okay. So anyway, getting back to like coming back to where we're working at. So let's just say we have one over omega JC.
Okay.
Omega is just 2 pi times F. That's still multiplied by J. That's still multiplied by C. And C is what did we say? 75 nanofarad. You said 75, right?
75, yeah.
Yeah, so we have 75 nanofarads. And that's all underneath one. Oops.
Now we were using 75 megahertz. No, you're right. We were using, yeah, okay, no, I missed that. Yeah, okay. It was 354 megahertz. Okay, go ahead. Nanofarad's very, very small, ain't it?
Yeah,
Yeah,
but it
man.
makes a difference at high frequency.
Yeah.
So we have 2 pi times 354. Oh, hold on, let me do my parentheses. 2 pi times 354 e to the sixth times 20 or 70, 75 e to the minus ninth, and then do 1 over that. I'm gonna change this to picofarads because this is a really small. This is a really small impedance.
Okay, picofarad, okay.
It's almost zero.
Uh-huh.
but I think picofarad should make it a little bit different. Okay, so yeah, that's it's still small, but it's at least more of a reasonable value.
Okay.
And then you end up getting about 5.995. That's negative J ohms. So then our total would be, instead of plus or minus, now we know for sure it's minus because it was a capacitor. So minus 5.995 J, and that equals the impedance of the antenna equals 253 plus 5.99 J ohms. So that's how that's solved. Anybody out there who's solving it later, y'all can check me.
Okay. Times 250. Okay.
Let's see. So there's types of antennas. Isotropic. This is theoretical dipole. This is the most common. Um, Use two poles, pieces of wire extending from the transmission line at the center feed. Best when this is when these dimensions are followed. A small dipole is short compared to lambda. L is less than lambda over 10. Like the length is less than lambda over 10. D is 3 over 2 sine squared theta. Um, Finite length dipole, assume a sinusoidal current. So IZ is I naught times sine times 2 pi over sine of 2 pi over lambda times L over 2 times, I think that's the magnitude of Z. Yeah, magnitude of Z. There's a half wave dipole, which is L equals lambda over 2. 377 times the current naught squared over 8 pi squared times cosine of pi over 2 cosine theta squared over sine theta squared, used to plot the out pattern. Antennas above a ground plane, you have reference points. Allowed for monopole antennas, quarter wavelength long.
What
Ground plates,
the
sigma is
power?
infinity, quarter wavelength. Quarter wave monopole. The pattern looks like this. Then you have horn antennas. Bigger reflection, bigger direction. So you have effective area equals this. How waveform illuminates. So once again, you have pi d squared over 4. Nu I. G is 4 pi over lambda squared times the effective area. G is this times this. So and this is efficiency. This is efficiency. So at 95%, you have a D of 0.5. Frequency is 12 gigahertz. Lambda ends up being 2.5 centimeters. So then, just like this equation here, you have 0.95 times pi times 0.5 over 0.025 squared. Wham, bam, thank you, ma'am. Then you get that in dB. and that's 10 log of this value, and that gives you like 35.7 dB. Sigma at 3 dB is 1.2 pi or lambda over d, or 70 over d degrees, lambda over d degrees. So yeah, that's everything that we learned for the most part. Then we have the microstrip patch antenna. I believe that these equations will be given on the exam. Like I believe they'll be given on the exam. But I don't want to overstimulate my mind. Trying to make sure I'm doing okay. Trying to make sure I get enough rest and I don't end up cramming. So
Yeah.
that's gonna do it for this episode of study session. So I appreciate all y'all for joining. I appreciate anybody who joined in. I appreciate you, Granddad, for coming on to learn, asking questions to make me explain stuff. Shout out to Bree. She was here as well. Thank you for coming on here. I don't feel ready, but I know I'll be ready. I don't feel ready, but I know I'll be ready. I think I don't feel ready because I've been studying little by little, so it hasn't hit me that I know it all. But I have faith that I'll be ready when the time comes. Exams at like 1 p.m. tomorrow, so after the exam, I don't know. We'll see. But with that being said, I want to say thank you guys so much for watching this video and stream. Thanks for studying with me. If you liked it, give the like button a nice slap to the face, like another person. And I'll see all you guys. So I want to do the 5 cards on the wall next time. So I'm gonna end the stream now. Also, shout out to my grandma. She's on the stream now.
Yeah, don't you see him?
So yeah. So
Okay, all right, we're
I
praying for
appreciate
you,
y'all.
okay?
All right.